I'm Kavya Kopparapu. I'm 16 years old and a junior at Thomas Jefferson High School for Science and Technology. And today I'm really excited to share my research with you and show you the power of artificial intelligence in diagnosing diseases. And so before I jump into the research, one of the things I wanted to share with you all is what I've kind of learned over this last year of doing this research. And it's that the field of medical diagnosis is full of what ifs. What if I had been diagnosed early? What if I didn't have this disease? What if there was a better treatment available? And we can use artificial intelligence to reduce those questions and get medical diagnoses to people who don't have access to it usually, or develop new treatments by identifying new methods using artificial intelligence. And so this talk is going to be a little bit different than maybe some of the ones you've seen earlier today and earlier during the conference, because I'm going to essentially pose you a hypothetical. What if you wanted to do a project in diagnosing diseases? And I'll walk you through what my methodology was in creating Diagnosis, which is a platform for diagnosing diabetic retinopathy on your smartphone. And so the first step is to develop a vision by identifying a problem. And for me, it was more of a personal connection because my grandpa has diabetes and his eyesight has been deteriorating a lot. And so being able to make a connection between you and another person is one of the most important things about being in this field. And so step one is identifying a problem. And so the problem identified was diabetes. There are 415 million people across the world with diabetes today. And 80% of these patients live in rural or developing countries. And there are over 50% of these cases that remain undiagnosed due to a lack of diagnostic tools in these areas, whether that be trained doctors to be able to go out into the field and diagnose patients in like slums, or just having an ophthalmologist to patient ratio of over 1 to 1,000, so not having access to a diagnosis. And because of these things, diabetes is the leading cause of preventable blindness and blindness among working age adults across the entire world. So there's obviously a problem here of diagnosis because the treatment for diabetic retinopathy has been very established, but getting access to a diagnosis is a problem. And so here I have a picture of diabetic retinopathy, which is a symptom of diabetes in which high blood sugar damages the blood vessels in the retina. And you can see that there are a lot of symptoms such as aneurysms, hemorrhages, growth of abnormal blood vessels. And these are all diagnosed through retinal scans, through fluorescent angiography, which is mapping the blood vessels in the retina, looking if there are any abnormal growth. And all of these need to be performed by, obviously, a trained doctor. And so the question I wanted to pose is there a way that a minimally trained medical professional could deliver the same diagnosis with comparable accuracy from a fewer amount of tests that are performed today? And so just going to go through a few more statistics. And so here you can see a graph. It's a little blurry, but you can see that the x-axis is the number of years that a patient has had diabetes, and the y-axis is the percent of those patients who have developed diabetic retinopathy. And you can see that after around 25 years, 100% of patients have developed diabetic retinopathy. So this disease is not avoidable, but it can be slowed down through early detection. And so that's the problem I'm trying to tackle. And so here's another graph that shows the projected populations of patients with diabetic retinopathy in the United States. And so you can see it is only continuing to go up. And so because of this, early detection is definitely a problem that needs to be tackled. And so the next step is outlining current challenges. What are the deficits in the current technology that can be solved using artificial intelligence? And so here I have kind of like some information on the different problems that I was trying to solve in diabetic retinopathy. And so one of them is how expensive the diagnosis is. So in the diagnosis, you require a trained pathologist. And instead, how about using a medical practitioner using a smartphone, a device that almost everybody has and is very ubiquitous? And inefficiency. So if you have an area where you have one ophthalmologist per 1,000 patients. How is that one ophthalmologist going to be able to see every patient in a limited amount of time? So instead of having that one ophthalmologist go to every patient and diagnose whether they have diabetic retinopathy or not, maybe recruit medical practitioners who can go out into the field and perform initial triaging and bring the patients who really need help to the ophthalmologist. There's also obviously there's also a lack of pathologists. So their ophthalmologist to patient ratio is 1 to 1,000 in many of these areas. And so having a diagnosis performed by someone who can be trained in an hour or 2 hours to be able to do this procedure is very crucial. Finally, the tools required currently to diagnose diabetic retinopathy are numerous. So it requires things like retinal scans, angiography, optical coherence tomography, which are all things that like, for example, map the thickness of the retina to see if there is fluid buildup or to see if there is any excessive blood growth. And instead, combining all of these tests into one test, just looking at a retinal scan and developing a diagnosis from that. So essentially, it would eliminate the need of a lot of bulky equipment, like the equipment you use when you go to see your ophthalmologist or your optometrist, and eliminate all those tests and combine them into one. And so develop a problem statement. So the current technologies, there's no system that can inexpensively take an image of the retina and then automatically output a diagnosis. And so creating that system would allow the earlier detection of diabetic retinopathy. It would prevent permanent vision loss, and it would decrease healthcare costs for millions worldwide and give a diagnosis to patients who really need it. And so the next step is to develop a solution. So looking at different features and technologies that are state-of-the-art today and putting them towards this application. So here's an overview of the system I have developed. And so you can see that you first take a patient, and the patient needs to get their retina image. And so what's a low-cost way to do that? So if you think about the most low-cost piece of imaging equipment you have today, it's probably in your pocket. It's your smartphone. And so developing an attachment for a smartphone that will allow a medical practitioner to take an image of your retina. And then you need some sort of user interface. How is this retinal image going to be analyzed by an algorithm? So here you can see that there's a smartphone running the application, and so it serves as an interface for the incoming information and the analysis of the information and then the output of the information. And then so you can see now the image that has been taken needs to be analyzed. And so using artificial intelligence and deep learning, we can analyze those images and then output it with other information, such as segmenting out microaneurysms or blood vessels so that doctors don't, when they confirm the diagnosis, don't have to do additional tests. And so the next step is to identify a data set. And as all of you probably know, your artificial intelligence model is only going to be as good as your data set. It's going to be as applicable as your data set. And so the question to ask is, what type of data best represents the disease? And so in the case of the diagnosis system, there is a database from the NIH called the NIH iGene, and in this database they have thousands of images from all different types of eye disorders. And so they have over 34,000 images of diabetic retinopathy patients, positive, negative, and all of the different array of how severe they are. And so using this data set, we were able to divide it into diabetic retinopathy positive and diabetic retinopathy negative. And so what's special about this data set is that it's very reflective of the real world conditions. So the data set has around 60% normal eyes and 40% affected eyes. So if you took a data set that was split 50-50 or was not like disproportionate, then you wouldn't be reflecting the real world conditions. And that would make your algorithm not very applicable in the real world. Also, there was a lot of variation in the types of instruments they used to capture the images, the ages of the patient, the genders of the patient. So it's very reflective of real world conditions. And finally, in the data set, there was a lot of imperfections. As you'll see in this next slide, that there's like overexposure, underexposure, and that was actually really helpful, and that's what I was looking for in a data set. Because without these imperfections, when you take it out into the real world and you take an image with a little bit of glare, your algorithm will be like, I don't know what to do now. So having this type of variation built into the data set is very valuable. And so as you can see here, there are some overexposed images, some images with glare and focus problems, some images that are underexposed, and some images that are normal. And so having this type of variation in a data set is very useful. And so the next step is to determine what artificial intelligence model would be best suited for my data. And taking all of the different types of models, there are so many out there, and determining which ones would be best. So for example, I had image data, so taking that, a neural network, a convolutional neural network, is very specialized for image data, and so that was what I determined to be best for this project. And so a little more information on the specific model I used. I used the ResNet 50 convolutional neural network. So when I started this research a year ago, the ResNet 50 had just won the ImageNet challenge. And so it was the state-of-the-art convolutional neural network of the time. And it's really funny to say that because artificial intelligence moves so quickly. Every year you get a new model that's the current state-of-the-art. And so what was really special about this model is that it had 152 layers, which was a huge number of times larger than the model that had won the previous year. And so it was capable of doing very, very deep learning. And so now that we had this data set with a lot of variation, we wanted to try to standardize it. So doing some pre-processing, such as one of the most important things was that taking the image, the original image, which was very high quality because it was taken by a retinal scanner, and rescaling it to a very small size, so 512 by 512. And we did that because if you take a high quality image of the retina of the entire view, that's not reflective of what you would get on a smartphone. So taking the data set and adapting it to your application is also very important. So another pre-processing step was subtracting local average color, so very simple edge detection essentially to bring out the features. And also implementing something called cyclic pooling, which you're probably familiar with, because it doesn't matter what orientation the eye is in, it will always be diabetic retinopathy positive or negative, no matter what orientation it's in. And then feeding that into the neural network and getting a diagnosis. And so one of the things we did when we worked on this is that we tried to go for higher sensitivity, higher specificity, sorry, because if we told someone that they did not have diabetic retinopathy, we wanted to be sure, rather than telling someone, you have diabetic retinopathy, you don't have diabetic retinopathy, and then, oh, that was just a mistake. You really do have it. It's better in a triaging environment to tell someone that you have diabetic retinopathy and then have the doctor confirm that that's wrong, rather than send someone away because the algorithm has determined that they don't have diabetic retinopathy. And so here's a little information about the model training. Obviously, you can see that the loss has decreased, the accuracy has increased, and the F1 score has increased. And then so here are the results of the predictive model. You can see that there's a sensitivity of 0.68 and a higher specificity of 0.84. And so again, that was chosen on purpose. And then the area under the ROC curve was 0.784, which can be compared to the random classifier line of y equals x. And so we found a study done by the NIH of ophthalmologists who, not knowing all of the patient information, whether they have diabetes or not, whether how long they have had diabetes, what are their family history, and having them diagnose a patient of having diabetic retinopathy or not. We got those data points and compared our sensitivity and specificity to their sensitivity and specificity, and found that diagnosis has a statistically comparable sensitivity and specificity to that of an ophthalmologist. So showing that machine learning and artificial intelligence can really create something that can be used at the same level as a doctor and be implemented in the real world. And so now that I've talked about the predictive model, I have to talk about all of the supporting technology. So that would be the imaging technology to be able to take a picture of your retina, and the mobile application. Just wanted to show you a few screenshots. And so a few requirements for our mobile application were that we were going to do our computation on a server because while neural networks have been optimized for phones, they're not, their computational power is so intensive, it would be best to do it on a server, and so that's what we did. And obviously, phones are very ubiquitous and relatively cheap, so I read a statistic somewhere that there are more people that have access to a smartphone in the world than do have access to clean drinking water. And so that really made me think that makes sense that you can use a smartphone for triaging in areas that people might not have access to a doctor. And so we also did some computer vision algorithms to further augment the data, like I said, segmenting out microaneurysms and editing the data. And so first, detecting whether the images that were entered were overexposed or underexposed. And you can see that through grayscale histogram analysis. And then seeing, is the image blurry or not? And if it's blurry, then we should sharpen it to fix it. And if it's not blurry, then just send it off to the neural network algorithm, which will do more pre-processing. And so here you can see some of our app screenshots. It's not yet available on the App Store, but we're still testing it. And so you can see here how there are a few options. You can take a picture through your smartphone, or if you have a retinal image or like a retinal scanner available, you can upload that image already. There's also the detection will tell you whether it's overexposed or underexposed, if you have a blurry image or you have a sharp image, and it'll tell you the diagnosis. So you can also see here that we segmented out the blood vessels and the microaneurysms so that doctors don't have to perform more tests for the patient and can go straight to talking about treatment. And so the final part of the system is an attachment for your smartphone to be able to take an image of your retina. And so the lens system essentially will replace the traditional equipment, the fundus scanners you see in ophthalmologist's office. And we used a very nice technology, which is 3D printing. And so 3D printing allows rapid prototyping. And if you're you can always send designs to different places and have them printed out instead of mailed. Also, it's very cheap and very light, so it reduces costs from the thousands of dollars of equipment you see in ophthalmologist's office to tens of dollars. And so there's also a common piece of ophthalmological equipment called the 20D lens, and so we had our system to fit that lens, so you don't have to buy any more additional lenses. So it's fitting what we already have. And so you can see a video here of the lens system, and you can see some screenshots. And so it's very specific. It fits a very specific phone model, but it can be implemented to fit other phone models. So right now it fits the Samsung Galaxy S7. And so you can see it there. There are a few lenses in there as well, but they're also very cheap. And so here, there's a little optics involved in this too, creating a ray diagram. And one of the great things about the smartphone attachment is that normally to take an image of your retina, because the light is so bright, you require the dilation of the retina, of the pupil. But instead, because of this system, you don't actually need that. So it cuts out 30 minutes of time for an ophthalmologist to have to dilate your pupil. And so finally, one of the last things you need to do if you're going to implement such a pathologist technology is to validate it in the real world. And so what we did for diagnosis is to create a collaboration with the hospital in India, which is called Aditya Jyot Hospital. And so they already have a program in which they triage patients in the slums of Mumbai, and they implemented the diagnosis device, into their system, and were able to reach many more patients than before. Originally, they were taking a motorbike and putting all of the ophthalmological equipment on that bike, and then going into the cramped spaces and going door to door to diagnose patients. And using this device, they're able to take something that they can just put in their pocket and take it everywhere around the city. And so the collaborators for this project are listed here. We collaborated a lot with the NIH for the data set, and with the Aditya Jyot Hospital for testing, and also at my own school, Thomas Jefferson, for the 3D printing and the other technologies. And so for this technology, its contributions to the field is that it performs at the same level of pathologists, which means that it can be implemented in the real world, and it has been tested. And it has a huge time and cost reduction. So taking a diagnosis time of 2 hours and turning it into a minute, taking technology that costs thousands of dollars and turning it into technology that costs $30. And it's portable and it's accessible and it requires very limited training. So everyone has a smartphone, and being able to take a device that is this big and put it in your pocket and being able to triage patients is very valuable in areas where there is a very high patient to ophthalmologist ratio. So the final applications of this technology are in initial screening in these underdeveloped areas, or having a second opinion in developed areas where pathologists usually get 1, 2, 3 opinions on their data before they start treating a patient. And finally, the system is very generalizable. So given the right data set, you can create a system that can diagnose all retinal disorders with just one picture. And so thank you, and I have time for questions, I think. So, does anybody have any questions? Yeah.
So in your validation in India, did you actually test it against the existing machines?
Yeah, so what we did is that they would take an image with our system and also take it with their original retinal scanners, and then they would have a pathologist grade it, and then our algorithm would give an output and they would compare it. And so far it has not been wrong. And they've tested, I think, around 15, 20 patients so far, and it's ongoing. So, yeah.
Where did you come up with this?
So my grandpa has diabetes and diabetic retinopathy, and so and because he lives in India, I was reading a lot of statistics about how there's not many patients who have access to a diagnosis and access to treatment. And so I thought there has to be a better way than what's implemented right now, which is trying to get the patients to come to the hospital or attempting to bring the hospital to the patient. So instead, developing a system that has a low-cost imaging device, a low-cost grading device, and is easy to use for someone who's not an ophthalmologist and can be interpreted by the patient as well. So that's kind of how I came up with it, yeah. Yeah.
What is your next target? I'm really looking forward to that.
Well, so I'm continuing to develop this because right now our sensitivity and specificity is comparable to that of an ophthalmologist, but we're aiming to have it statistically higher than that of an ophthalmologist. And also, I guess currently I'm working on another project which is detecting necrosis in brain images. So that's another thing. One of the great things I think about artificial intelligence and computational pathology in general is that it allows even a high school student to be able to work on a project like this. And you can't say that about a lot of fields of science. And so that's what I think is really special about computer science and artificial intelligence. Yeah.
Can you tell us a little bit about this Girls Computing League as well?
Sure. So it's a nonprofit organization that I started 2 years ago to support the interests of girls joining computer science. And so I noticed a really big gender gap at my own high school, and so I go to a science and technology magnet school, which is a public school, but we still have, everyone is really interested in computer science, just technology in general. But in my computer science classes, I've realized that there are 5 girls and 30 boys. And then as the years have gone on, it's become 2 girls and 30 boys. And it's just gotten smaller and smaller. And I've realized that talking to my friends, it's not because of a lack of interest. Like, everyone's really passionate about computer science. It's a feeling of, I don't think I can do this, or I'm not as good as the other people. Maybe I should try something else. So supporting the interests of students is really important. And so what my organization tries to do is get students connected with professionals in the field so that they can see themselves in 10, 20 years in a professional environment and say, I can really do this. And we do a lot of outreach with housing authorities, so girls who would normally not have access to computer science at school don't have internet access at home, but showing them computer science concepts and getting them interested. So, yeah. Does anyone else have any questions?